Okay, so we're switching gears today. We're changing topics completely. We're even changing book. So we're moving back from Enumerative Combinatorics Volume 2 to Enumerative Combinatorics Volume 1, Chapter 2. And we're going to talk about, I always get nervous when I'm about to say this word. Is it sieve or sieve?
Sieve.
Are you sure?
Sieve.
Sieve.
It's a sieve.
Sieve?
It depends
If
noun or
it's a verb or a noun, yeah.
So I never knew what this word meant. I learned a little bit when I was in Boston, and you know it's the winter, it's cold, and you have to find something to do. So I started playing hockey, and then in hockey, people are always screaming "sieve, sieve," and it took me like 2 years to understand what they were saying. And I guess a sieve is a hockey goalkeeper that doesn't ever stop any shots. I think. So. Sieve? Well, actually, what does the word sieve mean? I'm not sure that I know.
It's like a sifter, flour sifter,
Ah, okay.
and it goes through it.
Oh no, then I do know what. Then I do know what. Yeah, okay. So sieve, right? So it's you know, something that kind of stops some things but lets others through. That's what sieve methods are. So actually, I guess a sieve is a hockey goalkeeper that lets too many things through, but should stop some of them, right? Sieves should stop some things, but let other things through. Okay. So that's what sieve methods are about. So sieve method. And I should say that I think in Spanish this word is criba, but I don't know. I've never used that word in Spanish. I guess I just did. A sieve method is a way of, it's a method for enumerating objects by overcounting and then seeing how much you overcounted, basically. Then subtracting off what you didn't mean to count. So that's very vague, and there's a lot of things that people call sieves. And maybe the first, at least the first historical example that I am aware of is the Sieve of Eratosthenes. Eratosthenes. And this is coming from number theory. And this is a method for listing all the prime numbers between 1 and whatever you want. So let's see how many I can fit here. So 1, 2, I'm gonna write down. Let's do from 1 to 20. Okay? And the goal is to make a list of the prime numbers from 1 to 20. Okay? And so then it goes like this. First you let them all through. Okay, but we let through things that are not primes, and so now we want to sieve them. We want to stop some of them. Okay? And so you start and you say, okay, let's go from here, and then you say, well, what's the first number that I have not considered yet? 1. Is it a prime? Actually, I just learned from Harold Helfgott, who visited us a few weeks ago, that in Eratosthenes' time, actually 1 used to be a prime, but it got demoted to being not a prime anymore. So now we don't consider 1 a prime. So, okay, 1 is not a prime. And then we say, okay, what's the next one? 2. So 2 must be a prime because there's nothing before it that divides it. So 2 is a prime. But 2 also certifies that many other things are not primes, right? 2 certifies that 4 is not prime, that 6 is not prime, that 8 is not prime, 10 is not prime, 12, 14, 16. None of these are primes. Okay? So you stop some of them. Okay? But now we need a finer sieve, or we need to kind of apply all these different sieves until we get the right answer. So then we say, okay, we have 3. Well, 3 hasn't been scratched off by one of the previous numbers, so it must be prime. And then we go, okay, well, if 3 means that 6 is not prime, 9 is not prime, 12 is not prime, 15 is not prime, and 18 is not prime. All the multiples of 3 cannot be primes. Then I continue, okay, 4 is not prime, 5 must be prime because I haven't scratched it off, and so 5 is prime, and then that means 10 is not prime, 15 is not prime, 20 is not prime. And I continue, and I say, okay, well then 7 is prime, and then 14 is not prime. Not prime, not prime, not prime. Then this must be prime. There's no multiples on this list. This must be prime, there's no multiples on this list. This must be prime. And this must be prime. Okay? So this is kind of the first method for figuring out all the prime numbers from 1 up to n for some reasonable value of n. Okay? And that's more or less what we want to do in several contexts. Okay, so this is based on a very simple idea. Which is that, I don't know, let's say that you have some box of objects, okay? And then you have some properties that they might satisfy, like maybe property A, property B, property C. Okay? A, B, C. And so here's a little Venn diagram. And so I'm interested in knowing how many elements, and let's maybe call my set X. So how many elements of X are not in any of my sets? How many do not satisfy any of these properties? And this is just like we were doing here. It's like how many are not multiples of 2, not multiples of 3, not multiples of 5, etc. Okay? And so I start by saying, okay, well, first, let's let them all in. Okay? So I'm counting these guys, 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 and these guys. Okay? Every single element is counted exactly once in the size of S. Okay? But I don't want all of them, so let me subtract the ones that are in A. Okay? So, okay, this is going to be dynamic, so maybe instead of taking notes, you should just look at what I'm doing. So I'm gonna delete the things in A, so that means I'm not counting these anymore, not counting these, not counting these, not counting these. Okay? And then let's say I want to subtract the ones in B. And so that means that I'm not counting these, I'm not counting these, but now I subtracted too much, and I am kind of negatively counting these ones and these ones. Okay. Now let's subtract off the things in C. Okay, and so then that means that I subtract these guys off, but now I kind of uncounted these ones, uncounted these ones, and uncounted these ones again. So they're counted negatively twice now. Okay, so let me put a -2 here to signify that. Okay, and so I still don't have the right answer because I had everything, and then I applied I cut things out, but now I cut too much out. Okay, and now I need to make up for the things that I over subtracted. So now let's add in the things that are in the intersection of A and B. Okay, and so when I do that, then okay, the intersection of A and B is this, so that means that now these guys are now not counted, and these guys, which were counted -2 times, they're not counted -1 times. Okay? Now let's add B intersects C, and so that means that now I corrected this and corrected this. And finally, let's add A intersects C, which means that I corrected this, but I broke this. Right? This is now overcount. Okay? And so to correct for that, then I subtract that one off, the triple intersection. So I subtract this off, and then this means that I've counted the stuff outside and none of the stuff inside. So that's a formula. Okay, it's a formula that you might have seen before. It's often called the inclusion-exclusion formula. Okay? And in general, it says that if you want, so if you have some subsets, A1 up to A, doesn't really matter of course, but AN of some set X, and if you want to count the things that are not in any of the sets, then you can just do it in this way by first overcounting and then correcting through this alternating sum of, first the single sets, then the double intersections with a plus, then the triple with a minus, and so on. Okay? So what I want to do is that I want to do a big sum over subsets, which here I called, let's say, S1, S2, up to ST less than or equal to n. And then I count the size of the intersection, A S1 intersect up to A S T. But I need to put it with the correct sign, and that sign is -1 to the n minus t. Okay? And here t should be at least 1. So that I'm not putting the empty set here. So this right here is what we call the inclusion-exclusion formula. Okay. Maybe let's just give a quick proof of this. And it's basically going to be imitating what I just did here, but a little bit more abstractly. So I'm going to say proof. Suppose that I take some element of x, and let's suppose that it is in precisely the sets A sub J1 up to A sub J sub S. Out of the n sets, it's in precisely those. Maybe I won't use S. Let's use M. Okay, so it's in exactly M of these sets, and they are these ones. Okay, yeah.
I'm feeling uncomfortable with the subscript notation. I mean, it's fine. I feel like it looks weird.
It's a little bit ugly, but I think it's the best way of writing this actually. Unfortunately, yeah. So if we take an element of x, okay, and it's in precisely one of these, it's in precisely m of these sets, then let's try to figure out how many times I added it and subtracted it, okay? We counted it like this. We counted it in x, right? Then we counted it with a minus. How many times did we count it? Well, we counted it in AJ1, AJ2 up to AJM. Right? We subtracted it m times. Then how many times did we add it in the next step? In the double intersections, right? AJA intersect AJB. How many double intersections are there? Well, if I have m of these, this happens m choose 2 times. Right? Then in the third step, I subtracted it m choose 3 times, etc. Okay? And so you see, this is precisely the alternating sum of the binomial coefficients, which is 1 minus 1 to the n. I counted it 1 minus 1 to the n times. And if n is greater than or equal to 1, this is 0. Whereas if n is equal to 0, this is 1. Okay? And that means that if x is in none of the sets, I counted it once. And if x is in some of the sets, then I counted it 0 times. So that's correct. Okay? So So this proves this identity, but now I want to rewrite it in a way that's a little bit more useful or explicit as to how we actually use this. So, principle of inclusion-exclusion. Let A be a finite set, and let S be some set of properties that elements of A might have. They might or might not have these properties. Okay? So we're going to define F. Okay, so for some subset of the properties, we're going to define F of t to be the number of elements of A satisfying precisely the properties in T. So you satisfy exactly the properties in T and not the other ones. Okay? And let's define F greater than or equal to be the number of elements of A satisfying at least the properties in T, but maybe satisfy more of the properties. Okay? And so, of course, this is going to be equal to the sum over the supersets of T of F equals U. Right? If you satisfy at least the properties in T, then you satisfy exactly the properties of some set containing T. Okay? So I haven't said anything too intelligent yet, but the principle of inclusion-exclusion allows us to reverse and express the F equals in terms of the F greater than or equal. So this is the power of this method. And the fact is that the sum is almost the same, except that you just have to put the correct sign here. Okay. So if you think about it, this is exactly what I'm saying here. In particular, because it's a little bit more general, but in particular, what I'm saying is that maybe let's put a box around this one, which is more commonly used. Well, no, okay. So if I want to know how many elements satisfy none of the properties, then I should sum over all supersets of the empty set, but those are all the sets. Right? So I'm just summing over all subsets of S minus 1 to the U F greater than or equal to. This is bad notation. It's going to be like this. So what's the point of this identity? Why is this useful? The point is that actually, in many situations, it's hard to count things that do not satisfy properties, and it's easier to count things that do satisfy properties. And so what I'm saying here is that if I want to count the things that satisfy none of the properties, it suffices to count the ones that do satisfy the properties for every subset U. Okay? So it's like yeah, anyway, that's what it says. And the proof of this is just this. It's really the same statement, it's just kind of a different way of saying it. So I know that the first time that you see this inclusion-exclusion, it looks kind of overwhelming, and I think that the best way to clarify it is just to do some examples, and so that's what we're going to do for the rest of the hour, is just show some examples of how this works for particular combinatorial problems. Okay, so example 1. It's an example that is familiar to us. Derangements. Okay. So let me remind you that Dn is the number of derangements of n, which are the permutations of n, such that pi of I is never equal to I. Permutations pi of n having no fixed points. Okay? So this is the kind of thing where I'm asking you to count objects that don't have certain properties. Right? We don't have the property that pi of I is equal to I. And if you think about it, it's much easier to count those that do have the property, because if pi of I is equal to I, then you know where I is going, and I is staying put, and you're just permuting everybody else. And so this is one of those instances where computing the negative thing is difficult, computing the positive thing is hard. I mean negative in the yes or no sense, right? Not satisfying the property is harder to manage than satisfying it. So we're going to carry this out. So I'm going to do it this time I'm going to do it very explicitly in this language so that to make sure that it's clear. So I'm going to define a bunch of properties. So what are the properties that I want? Well, I'm trying to avoid n properties. Pi of 1 equals 1, pi of 2 equals 2, etc. So let's call those the properties. So these are the properties where S of I is the property that pi of I is equal to I. Okay? Yeah?
So for here, for S equals empty set, could that be a positive answer?
This is certainly a positive. I mean, do you mean that this is a positive number?
Well, yeah, number of elements says it's positive, 0 positive. But I'm just thinking in terms of definition set of properties that elements of A might have. So.
Oh, okay. That's a very good question. So the question is, what if I'm interested in not satisfying exactly these properties, or satisfying at least these properties, but what if I want to count things that might satisfy the properties, meaning at most you satisfy the properties in T, which would be called F less than or equal to T. And I'm glad you asked that, because we are actually going to address it later. So you'll see at some point I'm actually gonna change the order and I think address the question that you're asking. Okay, so I have my n properties, right? And so then I know that Dn is basically the number of elements that satisfy none of the properties. Right? But now I have a formula that tells me this should be the sum over all subsets of S of -1 to the n minus the size of the subset, and F greater than or equal to. Yeah.
So here S was S1 through Sn,
Mm-hmm.
but there S. I'm confused.
So S is my set of properties. I have if properties that pi of 1 is 1, pi of 2 is 2, pi of n is n.
So what's that S down there in that sum?
I mean, I guess I could. Well, I think I see what you're confused about. So I guess formally I should say that U is a subset of S. to make it match there. But I'm just kind of saying, well, subsets of S are the same thing as subsets of N. So I'm identifying this set with the numbers from 1 up to N. So yeah, thank you for pointing that out. And now that hopefully is clear, let's just consider sets of this, which is a little bit easier to simpler notation. Yeah?
But over there, you're raising -1 to the size of u, and here.
Oh, yeah, thank you. -1 to the size of u. That's what I should have done.
Yeah.
Yep. Yeah, I have it backwards in my notes. It's okay. Okay, so now the thing is that I claim that this is very easy to compute. Because what is this? These are the permutations that have at least these fixed points, right? So if u, so I'm demanding that the coordinates of u stay fixed, right? Pi of u1 is equal to u1, pi of u2 is equal to u2. The things in u have to stay put, and the other ones you're allowed to permute. Okay? And so that means that you just take the things that are not in u, you permute them. And then the things that are in u, you just leave them alone. Okay? Okay, so now let's just figure out what this is equal to. Now the nice thing is that actually this thing just depends on the size of u. And so let's give a name to that size. So let's say the size is k. K goes from 1 to n. Okay? And so I get -1 to the k times n minus k factorial. Now, how many times does that appear? That appears whenever I have a set u of size k. So that's just n choose k. Okay? And so, sorry, I'm feeling a little tight with my board here, but so let me just go up here. Number of derangements is what we're counting here. And so this, okay, well, this is n factorial over k factorial, n minus k factorial. So I get that this is equal to some, actually k equals 0 to n, right? Because this could be the empty set. So I get the sum from k equals 0 to n of -1 to the k n factorial over k factorial. And the n minus k factorial cancels with this one. And this is the expression that we had for derangements. Right? This is, and we said that this is approximately n factorial over e. And I should say that this is the more common way of deriving this formula. Actually, I can't remember now how we. Oh yeah, we did it with exponential generating functions. That was a nice proof where we just kind of said a derangement was a permutation such that there were no cycles of size 1. And then we used that to kind of give a fairly simple argument using exponential generating functions. But anyway, this is an argument that doesn't need exponential generating functions. Okay. So that's derangements. Okay. So that's the first example. Let's do another example. And this one comes from number theory. So Euler's totient function. That's another word that I've never know what it means except for it's this function. People also call it Euler's phi function. So what is it? Phi of n. So if n is a positive integer, this is going to be the number of things, number of integers k, such that k is between 1 and n, and the GCD of n and k is 1. So the numbers that are less than or equal to n and relatively prime to n. Okay? So this is maybe it's maybe a little bit less obvious how this what this has to do with inclusion-exclusion, and the thing is that we want to express this quantity in terms of like what properties should we not have. Okay, so what properties do you not want to have if you want the GCD of n and k to be equal to 1?
Prime in the factorization.
So the GCD of n and k is going to be equal to 1 if and only if the primes that divide n don't divide k. So P1 should not divide k up to Pt should not divide k, where n is going to be written like this. Okay, so if this is the prime factorization of n, then having GCD with n equal to 1 is the same thing as not being a multiple of any of these numbers. And now that's great because now we have a statement of this in terms of t properties that I should not satisfy, and so we can use the same procedure. Okay, so phi of n is going to be the sum over. So I'm going to already try to drop this S notation and try to. I mean, when you practice with this, you usually people will just, when you see it written, people will say by inclusion exclusion, and they'll just write the formula. And so we want to get to that point. So I'm going to be a little more implicit right now, and I say, well, so I need to sum over the subsets of my primes. Okay, so let's write it as. Just trying to use the same notation. Actually, I'm sorry. So just to match what the notes say, in the notes I used m here, and then so I say, okay, phi of n is the sum over this primes I1, IT. So I'm taking subsets of these guys, right? So I take a subset of them, then minus 1 to the number of elements in my subset, and f greater than or equal to u. Those are the things that do satisfy properties I1 up to IT. In other words, number of k which do satisfy the property, so they are multiples of PI1, PI2 up to PIT. Okay. For every subset of the primes, I need to count how many of my numbers are multiples of them. How many do have that property. Okay. And again, it turns out that this is much easier to count. And then you think about it for a second while I rewrite this. So the thing is that these are primes and they're different from each other, and so being a multiple of them individually is the same thing as being a multiple of the product. So this is the same thing as being a multiple of this number. Okay. And how many multiples are there of this number between 1 and n? Well, that's easy because, this is a multiple of this number, and so, you start non-multiple, non-multiple, multiple, non-multiple, non-multiple, multiple. So it's just n divided by this. That's the fraction of things that are 0 mod this number. So this is the sum over the subsets. And then you get -1 to the t. And now this is n over pi1 up to p. And again, here, notice it's important that n is a multiple of this. Right? And this is why this is an exact fraction. How do, let me say, if I call this number m, or not m because I'm already using m, let's call it q. Okay, if I call this number q, so I'm saying how many numbers between 1 and n are multiples of q? So you see, you start 1, 2, 3, up to q. Only one of those is a multiple of q. Then among the next q, only one of them is a multiple of q. Among the next q, one of them is a multiple of q, right? And given that the total number is a multiple of q, and a fraction of 1 out of every q of them is a multiple, then this is the number of multiples.
Should there be a condition on k?
Oh, yeah, this should be k, sorry. I'm counting the numbers k, which are multiples of this. Maybe that's why you were all looking confused. You should be confused if I'm writing something wrong. Okay, so that's the answer. Now, the cool thing about it is that this answer can be written a little bit more nicely as follows. You see, I have -1 to the t, and I have t factors. So let's bring those factors in here. Okay. So
Is that still n on top? Yeah.
this is still n, right? Because I'm counting numbers between 1 and n that are multiples of this. Okay. Let's take the n out here, because that n is common everywhere. And now I'm just going to write this as -1 over pi1, -1 over pi2, etc. Okay, so I just rewrote it. And again, trying to budget my board space here. Erase this stuff. Another thing is that actually here I'm summing over all possible subsets of this thing. And so it turns out that this is just the same thing as doing this. N 1 minus 1 over P1, 1 minus 1 over P2, up to 1 minus 1 over P M. Right? Because if I were to multiply this out, then how do I get a term? Well, I get a term by, in each one of these things, you either choose one or you choose the prime. And so, some of the ones, it's multiplicative, so you can just ignore it. So really what I'm doing is choosing some of the primes and multiplying the numbers minus 1 over that prime. So when I multiply this, I get exactly this. And so this is the formula for Euler's phi function. Cool. So maybe one thing that I want to mention is that, this is a class in combinatorics, but I think that the real masters of sieve theory are actually people that do number theory, particularly analytic number theory. When you look at I'm not sure if you remember this, but when Harold Helfgott came here and talked about his proof of the Ternary-Goldbach conjecture that any odd number greater than 7 can be written as a sum of 3 primes. A lot of these proofs start with some kind of argument with some kind of sieve, and then they have to work really hard and do like 200 pages of analysis to prove the results. And I mean, they're not only masters of sieves. They know. I mean, they do some very sophisticated analytic estimates and things like this. But this idea of sieves is just extremely prevalent in analytic number theory. That's if you like that, if you like this stuff, that's a good place to look. Okay, because I'm just showing you some simple sieve arguments, but this gets much more interesting. Okay. Okay. So let me go back to the question that Krista had now, which is, what if I'm interested in f less than or equal to here? Then how does that work out? Okay, and so the point is that there's a dual version of this, and essentially what I'm going to do is just take each inequality and turn it around and tell you that the same thing holds. But let's make sure that everything makes sense. So let A be a finite set, S is some properties, T less than or equal, T is some subset of S, F equal is going to be the same, but now let's define F less than or equal to be number of elements of A satisfying at most the properties in T. Okay, so you might satisfy T, or you might satisfy a subset of T. And so that means that this is the sum over subsets of T of things that satisfy exactly U. And then the question becomes, if you have this equality, how do you invert it? So you write F equal T equals the sum. Now I need to reverse this guy. Now here I'm dealing with subsets of T, and I reverse this one also. And here I don't really want to do U minus T anymore because U is a subset of T. And so maybe the obvious thing to try is to just reverse it. The remarkable thing is that this works. This is true. And in particular, when is this interesting now? Like, do I get an interesting formula for F equals empty set? No, I get the most boring formula, right? F equals empty set is the sum over subsets of the empty set of things that are satisfy at most the empty set. I get a complete triviality there. So what's the interesting thing here is if I want things that satisfy all the properties. Then I have to sum over all subsets of the properties, same as I have here. Minus 1 to the, now it's S minus U, and F less than or equal. And so this is maybe a more optimistic take on the inclusion-exclusion thing, in that now you want to find things that satisfy all the properties, instead of things that satisfy none of the properties. And of course it's a matter of linguistics, because saying that you don't satisfy that pi of I is equal to I is the same thing as saying that you do satisfy pi of I is not equal to I. So maybe it shouldn't be surprising that these things are so similar. Okay? But it's amazing how putting a no in front of a sentence can make it so much harder psychologically. So you should just know that there's these two things, and they're essentially the same. And if you can remember one, then the other one is just obtained by flipping the inequalities and making it work. And the proof is the same. Okay. And actually, from what I just said, I just proved that these two versions are equivalent if you just negate the statements. Okay. And I show you that because I want to show you it, but also because we're gonna now do an application where this dual version is a little bit more natural. So here's example 3 for today. Counting permutations by descents. And you might say we already did this, but I want to do something stronger than what we already did. Okay. So recall that the descent set of a permutation is the set of positions. So if pi is some permutation of the numbers from 1 up to n, actually, I don't want to make it sound like a group because it doesn't. The group structure doesn't matter here. So for pi, a permutation, and the descents are the positions such that the number in the ith position is bigger than the number in position I plus 1. Okay. Actually, I think I just called this d of pi. And then the number of descents we denoted like this. Okay. And so just to remind you, we actually computed this. So sum over permutations of q to the number of descents. We studied this. I think maybe we added one to the exponent, and we called this the Eulerian polynomial. And we proved several nice properties of it. So we already talked a lot about this problem and how you get that enumeration. But now I'm interested in a more refined version of this, because I don't want to count permutations just by the number of descents, but also by the positions of those descents. Okay. So now we count permutations by their set of descents. Okay, so let me say that beta of s is going to be the number of permutations of n such that the descent set is exactly s. Okay. So that's the number that I'm interested in computing.
Jimmy, D.
Oh yeah. Thank you. Actually, let's just call it des so that we remember that those are meant to mean descents. Okay. So let's try to do. I don't know. Let's say that n is equal to 9, s is equal to 1, 3, 5. 8. And let's try to see if we can come up with some very simple argument to give the answer. Okay. So what we need to do is a permutation from 1 up to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I have my descents precisely at 1, at 3, 5, and at 8. So I want to write down permutations that go down precisely in those positions. Okay? If I want to go down precisely in those positions, then that means that I should go up in the other ones. Right? So, these should be increasing, this should be increasing, this should be increasing. So what if I just say, let me just split my 9 numbers into a set of 1, a set of 2, a set of 2, a set of 3, and a set of 1. Okay? And then let me just say, well, let me take this one number and put it here, take these 2 numbers and put them here in increasing order, these 2 in increasing order, these 3 in increasing order, and this one in increasing order.
So you can't have 1 in the first position.
So here I'm not saying to put the number 1, I'm saying to put whatever the So when I choose this, that means that I end up taking my numbers from 1 up to 9, and I end up having like some number here, then 2 numbers here, then 2 numbers here, 3 numbers here, and 1 number here.
But the first one can't be 1.
Yeah. It's
So what you're saying is that this one, for example, shouldn't be 1. Why? Because if I put the 1 here, then this is certainly not going to be a descent. Okay, and that's the trouble. The trouble is that in this argument that I'm making, I mean, I can't do that thing. I can't do this, right? I can take one of these arrangements of the numbers from 1 up to 9 into these groups. I can put them into here, and it is true that I'm not going to have descents where I don't want to have descents, right? I'm going to have a sense here, a sense here, a sense here, because I choose to put these guys in increasing order. The trouble is that doesn't guarantee that I do have descents where I want to have descents. Right? And so that's why this problem is trickier. But, okay, so maybe this is not beta equal S, but this is what? What I did is that I just created something where I might have descents at S, or I might not. But I'm not going to have descents elsewhere. Okay, so this is true. So I call this alpha, but I like this one better actually. So beta less than or equal to S is going to be the number of permutations of n such that the descents are a subset of S. Yep.
Can you go over that one more time, why it's less than?
Yeah, so let me write the claim that if S consists of, let's say, S1 less than S2 less than S, let's see, what did I use here? K, then this is precisely the multinomial coefficient, and choose S1, S2 minus S1, S3 minus S2, up to n minus sk. Or like this, then sk minus 1, and then n minus sk. So again, why is that? Because in this case, this is S1, this is S2, this is S3, this is S4, okay? And so I'm saying, let me take my n numbers from 1 up to n and split them into groups. One group of size S1, one group of size S2 minus S1, one of size S3 minus S2, and so on. Okay? And now let me put each group in the permutation in increasing order. Okay? So if here, well, let's do an example. So if this was, I don't know, 7, and then these are like 4 and 2, and you can't see, let me draw the balls bigger. So maybe ball 7 landed here, then balls 4 and 2 landed here, then balls, I don't know, 1 and 8 landed here, then balls, what am I missing? 3, 9, and 5 land here, and finally ball 6 lands here. So the number of ways of separating into groups like this is given by this multinomial coefficient. And now I'm saying take this and introduce it into the permutation, one group at a time, and put each group in increasing order. Okay. And so I'm saying that the result is such that within each black group, that's increasing. So I don't have descents in any non-blue position, but I'm not guaranteed to have descents in the blue positions. Now, it's a bit unfortunate that in this example it did happen, that they're all in blue positions, but that didn't have to be the case. Right? For example, if I had put instead the 2 here, and the 4 and the 7 here, then the outcome would be 2, 4, 7, and I don't have a descent here. So what I'm saying is that my descents, at most, are the blue descents, but they're probably not all of them, and that's why that's not a formula for beta equal to S, but for beta less than or equal to S.
Okay, so I'm trying to like figure out what the wording for our definition over there, and so is this, we're thinking it's satisfying at most descents in 1, 3, 5, and 8, but so it could be descents in 3, 5, 8, it could be descents in 1, 3, it could be, that's what.
Exactly. Exactly. This is saying the descents are, any subset of 1, 3, 5, 8. There's 16 possibilities. Okay, so I have that formula, and now I'm going to use that again in a second. That's why I want to keep it there. Okay, so then I have a formula for beta of S, which is just the beta equal of S, and is given by this. Right? Yeah, so let me call S, again, S1 up to Sk. That's my set S. So I get that this is a sum over subsets of this, right? And so I write those as, I need to take a subset of the numbers from 1 up to k, and again, it's going to be a bit of unfortunate notation, but it is what it is. I have to write this. I choose some subset of the indices, and I put them in increasing order. And then I should write what? I should write -1 to the big set minus small set, k minus t. And then f less than or equal to, which is this stuff. So I get, and choose, and now it's not these guys, because I don't have all the S1s, I only have the SIs, right? So I get SI1, SI2 minus SI1 up to n minus SIT. Okay, so let's take the n factorial out. Actually, I'm gonna just write down a formula. And then we'll see why this formula is true. Because, this is a formula, it's a fine formula. It is what we wanted to find, right? This is the number of permutations with descents precisely at S. But I want to show you that I can rewrite this formula in a very nice way as follows. So I take out the n factorial, then you might not see this coming, but I'm going to write down a determinant. And my determinant is going to look like this. It's going to look like 1 over S1 factorial, 1 over S2 factorial, 1 over S3 factorial, etc. up until 1 over S3 factorial. Okay. Now I'm going to do 1 over S2 minus S1 factorial, 1 over S3 minus S1 factorial, up to 1 over Sk minus S1 factorial, and then 1 over S3 minus S2 factorial to Sk minus S2 factorial. So you see here I don't subtract anything. Here I subtract S1 in each factorial. Here I subtract S2 in each factorial. And I continue until in the last one I get 1 over Sk minus Sk minus 1 factorial. What do you think about the determinant? The determinant actually is, at this point, it's overly complicated, and actually it's an upper triangular matrix. So it can't be this, otherwise I wouldn't write it as a determinant. But I just want to write it like this so that you see that what's the main diagonal here. 1 over S1 factorial, S2 minus S1 factorial, S3 minus S2 factorial, like this. And when you do n factorial divided by S1 factorial, S2 minus S1 factorial, etc., you get exactly this. Right? So we're kind of in the right direction, but we only have one term, we need a lot of terms. And so it turns out that what you do is that you put ones here, right below the diagonal, and zeros everywhere else. Zero, zero, zero. And then you have 1 and this guy. Okay? So it's a matrix that is almost upper triangular, except that it has ones right under the diagonal and then zeros. Okay? So somehow I'm claiming that this determinant equals this summation. Okay, let's talk a little bit about that. I mean, this is one of these proofs that if you try to write down a formal proof, it will be completely incomprehensible. And really the right way to understand this statement is just to kind of stare at this determinant long enough that you believe it. Okay, and then you can write down a proof and it'll be incomprehensible. And so I thought instead of trying to write down a proof, let's just look at the determinant for this set and just see why this is plausible. So how does the determinant look in my example? Anyway, so that, punchline is that this is it. Before we go into the example, let me just say that well, this stuff was auxiliary, but I didn't really care about computing this guy. This is the one that I was after, and that's equal to that. So this is the theorem. Okay. And let's do an example to see why. I mean, basically, what's left in proving this theorem is to show that this determinant actually is equal to this. So let's write down this determinant for this set. Okay. So we have 1 over 1 factorial, 1 over 3 factorial, 1 over 5 factorial, 1 over 8 factorial. Then I have 1 over 3 minus 1 factorial, 1 over 5 minus 1 factorial, 1 over 8 minus 1 factorial. And then 1 over 5 minus 3 factorial, 1 over 8 minus 3 factorial. And finally, 1 over 8 minus 5 factorial. So those are the interesting terms, and then the other ones are maybe less interesting, but still very important. We put ones there, and we put zeros here. So this is the determinant, right? How do you compute this? Well, you're supposed to look at every way of choosing 4 entries that are in different rows and different columns, multiply those 4, put the sign of the permutation, and add all of that. Okay. Let's do a sanity check. How many terms does the determinant have? You need to choose 1 entry in each row and each column, so it's actually just a permutation, right? N factorial. And how many terms does this have? Actually, k factorial, because k is the number of things that I have here. It's k factorial. How many terms does this have? Well, I'm summing over subsets of k, so there's only 2 to the k terms. So somehow, part of this must be that many of these terms are 0. And that's not too surprising because we have zeros. So a lot of these terms are going to be equal to 0. In fact, most of them, right? Out of the k factorial terms, only 2 to the k are going to be non-zero. Okay, so the sum is over subsets of 1 up to k, right? And like I said, there is one term that we have correct, which is when you take this times this times this times this. If I take that, then that is going to account for the set, for the subset, which one? For the whole subset, right? 1, 3, 5, 8. Right? When the subset is 1, 3, 5, 8, then I do get n factorial over these guys precisely. So this main diagonal term corresponds to the subset 1, 3, 5, 8. Okay? But now, what about a subset of it, like the term 1, 3, 8, let's say? And again, the reason that 1, 3, 5, 8 gives me this is because I have 1, 3 minus 1, 5 minus 3, 8 minus 5. Right? Now, if I want to find the term corresponding to 1, 3, 8, then it should be 1, 3 minus 1, 8 minus 3. Right? So how should I do that? Well, actually, it's going to be a little bit more interesting to do this one, I think. By interesting, I mean harder. I'm not making it easier on myself, I'm making it harder on myself. Not by much, but I want 1 factorial, 5 minus 1 factorial, 8 minus 5 factorial. Okay. And I did already have 1 factorial, and I did already have 8 minus 5 factorial. But I don't want these guys, 5 minus 3 factorial and 3 minus 1 factorial, because 3 is not a descent now. So how do I get rid of them? Well, actually, there's only one way of getting rid of these 2 terms, which is to swap them for these 2 terms. And that means that instead of going from 5 to 3 and 3 to 1, I skip the 3 and go directly from 5 to 1. And then, to make sure that I have 1 fewer term, I just multiply by 1. So it's very convenient that that 1 is there, and it just kind of doesn't get in the way. And so now, these 4 terms give me 1, 5, 8. Okay. And should we do one more? Like, it's another color that I have anywhere here. This black is the only one. So what about 1 and 5? Then what I want is I want to have 1 over 1 factorial. And I also want to have this 5 minus 1 factorial that I had. But I don't want to have the 8 minus 5 factorial and the 9 minus 8 factorial. Wait, did I? Oh, I missed a row and a column. Right? This was supposed to go all the way to... Oh, no.
And
actually, yeah, I am missing one column because I wanted to have n minus sk here as a possible thing. So I should have 1 over 9 factorial, 1 over 9 minus 1 factorial, 1 over 9 minus 3 factorial, 1 over 9 minus 5 factorial, or 1 over 9 minus 8 factorial. And then 1, 0, 0, 0. And still, the blue thing works. I just needed this term also, right? Because the last term is n minus the last one. The red one, okay, that's still the red one. And now what I'm saying is that let me take my red permutation from here to here to here to here to here. And now I say, well, I don't want 9 minus 8 and 8 minus 5. I just want 9 minus 5. So instead of these guys, we're going to swap, and the only chance I have is to swap them for these guys. And actually, I'm supposed to take this guy that was also in the red permutation. And this is basically the argument, okay? I mean, so from this you can then write down a proof, but like I said, I think it's just clearest to look at it and see how it happens. Okay. But again, okay, so maybe one thing we're thinking about is where are my ones that I chose? Okay. I mean, let me say even a little bit more about how to make a proof of this. Look at the black permutation. Okay, by which I mean the black terms here. What columns did I choose the ones in the black permutation? In the black permutation, I chose this one, and I chose this one, which are the column from the 3 and the column from the 8. And these are precisely the guys that are missing. Okay. What about the red one? In the red one, I only chose this column to have the term equal to 1 here. And so, and this corresponds to the 3, which is the missing term. Okay. And so to be a little bit more precise about what I'm saying that if you want to get this term for this subset, then what you do is that you look at the missing columns. Sorry, you look at the missing things that are not one of the i's, and in those columns you choose the ones. And then you can see that in the remaining columns, the only chance you have is to take the main diagonal. And the main diagonal is going to give you 3 ones. Okay. Yeah?
So you were saying there are 2 to the k terms in that sum, right?
Mm-hmm.
And so, is what this is saying is that the 2 to the k sums, the 2 to the k terms in that sum are when your product over here of possible factors is non-zero.
Exactly.
It does not.
Exactly. So so what I'm saying is that in principle this should have k factorial terms, but in practice only 2 to the k of them are 0. Okay. And let me just close with one corollary of what we just did. And again, remember, I should have put here 1 over n factorial, 1 over n minus 1 factorial, etc. But maybe what I want to do instead of trying to fix that is I just want to show you an interesting corollary of what we just did, which is that let's look at this shape. 1, 2, 3, 4, 5. Okay. Let's look at the ones that are not 0. These are the non-zero entries in that matrix. So now, for example, let's look at the red product. Instead of putting a circle, I'm going to put this. Actually, I don't know if this picture is any good, because I don't know how to draw chess rooks. But you see, these are rooks. Pretend these are rooks. I think maybe this is not a great picture of a rook. But what is a rook in chess? A rook is something that attacks its row and its column, right? So in order to get a minor there, you need to choose n rooks that don't attack each other, right? And so the corollary of this proof is that there are precisely 2 to the n ways of placing n non-attacking rooks here. And it's 4. Right? Because each way of doing that is going to give me each one of the non-zero terms of this determinant. So out of the n factorial possible terms, I get precisely the 2 to the n corresponding to the 2 to the n placements of non-attacking rooks. Maybe let me just say very briefly that actually I mentioned this just to kind of pique your interest, but the next section in the book is about rook placements, and I'm not going to talk about it. So I'm sorry if you love this, but you should read it. Actually, I'm going to skip the section on non-attacking rooks, but the point is that for any board you can ask how many ways are there of putting rooks on it, and it's a nice theory. Okay. I think we should get going, but I'll be happy to answer any other questions that you have. Let me just start shutting down here.
So I have a sort of naive question, I guess.